Hi everybody, this is Tor Storley and I am back with another video. So what I want to do in this video is to introduce you to numeric conversions and how it's being used by the computer, which is kind of important to understand for good management of memory allocations. Now, a lot of times in a lot of programs, you're getting spoiled because there is the garbage collector who goes around and collects unused memory. Instead of copying it all the time and using more and more resources as you go in your program, you might just set references to an address that holds the values you're going to be using. So what I want to do is I want to take it down a little bit to a more lower level and show you the numeric conversions and how the computer utilizes these different numeric systems, which really helps to understand when we're getting into things like pointers and references, etc. So I created a couple of documents here. This is an introduction to understanding number systems, and I generated these documents with the help of Claude Sonnet, and I put a reference down here on the bottom. What I did was I saved it out as a Quarto document so I can have these nice little call types, and I'll make that available on my GitHub repository. So let's just kind of go through the overview of these numeric systems. You can see that it uses different kind of number systems because depending on what it's used for, the computer itself will use binary numeric systems. Me and you will try probably to look at decimals because, so whenever you print out something, you see it in decimals. You don't want to see ones and zeros. At the hardware level, as you can see, the computer operates on a binary level, on and off, ones and zeros. We'll focus on three number systems in this part of the videos: binary, hexadecimal, and decimal. Now, these different systems use something called a base. For binary, it's a base 2, meaning the on-off type of switching. For hexadecimal, there's a base 16. And in decimals, it's using a base of 10. This becomes important when you do the calculation or converting from one to another because you're going to have to use these bases. As you can see here, for binary, which is basically the low level of the computer's hardware being used at ones and zeros. So for CPU instructions, for memory storage at the bit level, network protocols at the packet level. So it's very low level internal workings of the computer and its processing. For hexadecimal, you see things like this, which is hexadecimal representation of binary information. For example, when you look at color codes, you're using hexadecimals. You've probably seen that many times for HTML documents, etc. And machine code and assembly languages, debugging and memory dumps, character encoding like Unicodes, you're using this type of representation for a letter A. The hexadecimal is a compact way, therefore, for humans to read and write binary. Each of these hex digits represents 4 binary bits. Here's an example. Because there's exactly 4 bits in the hex digit, this is a hex digit and this is a hex digit. Therefore, there's 4 of them in each. So you have 1111 and you have 1111. Therefore, that's an F and an F. This is from binary and this is in hex. And then you have decimal. And decimal, of course, is for user purposes mostly. You display it and print it out. And in programs, you write numbers. You don't write hexadecimal representations or binary representations. How do they relate then? Well, we already looked at the binary to hexadecimal. You have the 4 bits like this in groups. And each of those will be a hex representation of that group. The hex digits spans from 0 through 9. And then it goes from 10 through 15. So as you can see here, if it's an A, its representation is a 10. And if it's an F, its representation is 15. So it's a short way of writing those numbers here, 10 and 15, like this. So this is the binary format for 10. This is the binary format for 15. Okay, binary to decimal, again, we're not going to dwell on this because I'm going to show you some better examples here. And then you have decimal to hexadecimal. And of course, we go both ways here. So hexadecimal to decimal, decimal to hexadecimal, etc. What I want to look at next then is actually examples of how this can be calculated. And then I'll also show you how you can visually see this on your computer. So I have this document where we go through a few examples on how this can work. And I laid out a few URLs. So if you look, I'm going to be able to cover decimal, hexadecimal, and binary number systems, and vice versa. I also include some code in this document. As you can see, this is the example we're going to be basing it on. It's a very basic array in Go, where you import your main package and you import the FMT library. You create an array in the main function. Well, you should be familiar with this if you watched my previous video, how to set up Go in Visual Code. Here I'm simply creating an array of 5 elements, and here is the numbers that I'm putting in. And then I just print out whatever is here. So what I'm saying here is that you can run Go code here at this address, you can run C++ code at this address, and you can write the Python code in this address. Now, what do I mean by that? Well, in this document, as you can see, I'm showing you calculations, but you can also do it in code. I created this Quarto document, but notice I have Go code, so you can try this out for yourself in Go. You can try it in C++ if you like C++, and you can try it on Python if you prefer that. So for each one of these types, I created a code example. So you can try this out. So let me cover the first one first, and then I'll show you how to use it. Here you can see there's a Go array, and we're looking at some numbers, and these numbers I'll be using within this explanation. So starting with hexadecimal to decimal conversion, here is a hexadecimal, and the hexadecimal starts with this 0x. But for purpose of us converting this, we're going to ignore that, and that's why you saw in the code I strip out this 0x if you put that into the string that you're passing into the function. I don't want to use that part of it. But the hexadecimal numbering system is 0 through 9. So that's 10 numbers, if you will. Those are simply 0 through 9. You use it the way it is. When you get to a 10 here, you're going to use an A. When you get to 11, you're going to use B. So it goes all the way through 15. C12, D13, E is 14, and F is 15. So when you're given a number like this hex number here, there's 8 digits. If you remember, the hexadecimal uses a base of 16. So we got to use that base in order to compute this stuff. And also, you usually work backwards here. What I was saying is that the C here is going to be the last representation of a digit in this hexadecimal string. However, you'll be using the first position, meaning the 0 position. Anything raised to the power of 0 is 1, okay? So you can see here, position 0 through 7. So the first one, because we're going to read it backwards, is 0. The second one is 1. So therefore, you can see that 0, 1, 2, which is this one. And then you have F up here. And you can see that's position 4 and so on. So basically, we're setting up the whole number system here with these digits in hexadecimal, but then we reverse it because we start at the end and go in this direction. Now, just so I can say this, you can multiply this up and use this, or at the end of this document, if you look down here, I've done this for you. We have this table. So instead of you doing each one of these operations, you can simply grab the number here and use that. So with that in mind, when you go down here, you can see the calculations. So position 0, which is the last digit here, C, that's a 12. Why is it a 12? It's a C. And if you recall, a C is really 12 here. So the decimal value is 12, with hexadecimal digit is C. Raised to the power of 16 to 0 is 1, because anything raised to the power of 0, as we said, is 1. So therefore, your calculation becomes 12 times 1 is 12. And then you continue with the second digit up here, which is an 8, so you leave it the way it is. 8 times 16 is 128. And you continue like this all the way through till you get to the last one, which will happen to be a 0, which is this one. I'm sorry, it's this one because you're going backwards. And once you get that, you're getting a simple 0 because anything multiplied by 0 is a 0. So now you can sum them up like this. And the number you're coming up with is 19,899,788. So that's the answer of this, stripping out these first two digits. Now, does that make sense? Well, let's look up an array here. Notice, here is the same number. So that was the first one in our array. So in other words, if you did it the opposite, you would expect to take this number, you should end up with this hexadecimal. All right, so that's the first one. And if you want to test out the code in Go, you can use this function. So the way that works is, let's just take a look at it. I'm going to open up 3 environments. So I'm going to open up Go. So here is the Go code. Just go and copy it. Go to the Go playground. Just select everything and delete it. And one thing you might want to do here, because it tends to be kind of, you have to scroll a lot, just drag this guy up a little bit and drag this guy up a little bit so you can actually see the whole screen. Okay, so now here's the function. We can run it in the latest version of Go, and it's creating a temporary executable. And notice, it returns that decimal number just the way we did in our calculation. Now, we can still do the same thing in C++, so I can copy this code, go here, select whatever's there now, delete it, save it, like this, and run it. And if you run that, it's going to make another executable. So it compiles it, and notice you're getting the same number down here, just like you did. Finally, then you can go to Python, copy that, go over here, and then say run code. You can see that it returns the same thing here as well. So that's how you can run the code snippets that I provide you with in these documents. So I'm not going to go through the other examples. You can do that yourself. But I just want to show you how you can actually test this out and try some other combinations, if you will. So the next one then is decimal to hexadecimal. Let's take the second number in the array, 222,222. So that's this number right here. We're going to repeatedly divide by 16 and record the quotient. Now that would be the whole number we're ending up with. Then we're going to have a decimal portion of a number, which is called a fractional remainder. We're going to multiply that fractional remainder by 16. So the first one we divide, and the second one we multiply. So let's see what that will look like. So you start with a number, you divide on 16, this becomes the quotient, okay? So the whole number would say 13,888.875. That will be the actual number. So we are taking the whole number portion of that number, put it in here, and then we take the remainder, which is this fractional part, and we multiply by 16. And when you do that, you're getting a 14. And if you recall from above, in that display for a hexadecimal, 14 is E. But we're going to read it backwards, so you can read from the bottom to top. When you multiply this through, you take the next number you're ending up with here by taking this quotient, divide on 16, you're getting this. You're getting just .0, so there's no fractional here. So the fractional multiplied by 16 is simply 0. So the whole thing here becomes 0. So now it's a matter of just reading the number backwards. So you're getting 3640E. You can see the calculations over here, okay? And that ends up being, when you sum it up, 222,222. Here's the code examples for this one. Here's the Go code. Here's the C++ code. And here's the Python code. All right? Next one is binary to hexadecimal. Now, this can get confusing, but once you've done it once or twice, it shouldn't really be a big deal because you can easily create some kind of table structure. Binary numbers has 14 bits, right? In this case, this is a 14-bit. We need to have 16 because we wanted to convert it into a base of 16. So in order to do that, we'll have to add 2 leading zeros here in front of this guy here. Now we can get groups of 4. So we have 4, 8, 12, 16 is what we want. And each one of these 4 bits represents a hexadecimal digit. So when you have the binary to hexadecimal conversions, you have a base 2 number system, as you can see here on the screen. And therefore you're going to raise it to the power of 2. So we're reading backwards. So you start at the rightmost position. That becomes 2 raised to the power 0, which we know is going to be 1. The next position becomes, because there's only 4 in each digit, right? That'd be 2 raised to the power 1 is 2. Then you have the next position to the left is 4, and then finally then you have an 8, which is 2 raised to the power 3. So remember, we had this binary number. So if you start here at the first position, but you have to read from right to left, okay? So you have to go like this. So we know that this is the first position, 2 raised to the power 0 is 1. This next one is 2 raised to the power 1 is 2. And then 2 raised to the power of 2 is 4. And 2 raised to the power 3 is 8. So this is a 1, this is a 2, this is a 4, and this is an 8. Then it's a matter of seeing on and off switches. You only care about the ones because they're positive. So we can sum this up. So we can say this is a 1, this is a 2, 1 plus 2 is 3. So the first one therefore becomes a 3. Why? Because these zeros here are not activated. Only the ones are activated. The second group here, you can see, is 0, 1, 0, 1. So that means the 8 is 0, 4 is active, 2 is not, and 1 is active. So you have a 4 plus a 1 is 5. So the second therefore becomes 5. And then you can continue, but here you have a 1, 1, 1, 0. So that means 8 is active, 4 is active, 2 is active, 1 is not. So that's how you end up with 14. But remember, in hexadecimal, a 14 is an E, okay? And finally then, the fourth group is 1, 0, 1, 1. This one here. And that one is 8 plus, not 4, but 8 plus 2 is 10, plus 1 is 11. And in hexadecimal, it's a B. So the final result, therefore, is going to be a 3, a 5, a 14, and a 11. So that's how you can think of this in forms of binary to hexadecimal. So that's this one here, and your prefix is with the 0x. If you don't want to calculate this like this, you can simply look up the number. So here is 0011. What is that? Well, that's this one. 1110, 0, that's this. That's your E. So you can simply read it off. But you can also calculate it yourself by doing the pluses. And here you got hexadecimal to binary conversion. Here's the hex number we want to convert. And we're going to make groupings of 4, remember? The first 2 goes away. We got a 3, we got a 10, we got a 7, and we got a 15. So we need to figure out what is the equivalent of these guys. Well, you could do it the long way like this, or we could simply look it up, right? So what is a 3? It's this one. The next one is an A. So what is the 10? Well, that's this one, and so forth and so on. So when you do that, there is your answer right there. So here's your 3. Here is your 10. You get the idea. You can study up on this, but I just want to point that out. So you can simply use these tables if you want to look it up. Here's the Python and Go and C++ examples for that one. Down here is decimal to binary. So you're starting with a decimal. And to bring it to a dynamo, you do kind of similar to what we did before. Dividing on 16 and then multiply the fractional portion by 16 to get the remainder. Here we do it by 2. So you start with a number that is your decimal number, 35554, which is a number from our array up here, which is the third one here. So if you look down here now, number divided by 2 is this 0.0. So that's the remainder. That's the fractional portion. So it's when you do this calculation, you're getting 17,777.0. Anything multiplied by 0 becomes 0. Second one, you take quotient here, whatever it turned out, the whole number, divide on 2, so 888.5. So you take the fractional portion, the decimal portion of it, and multiply by 2, and you're getting a 1. Because remember, we're doing the 2 stuff because we only want off, on. meaning binary outcome, 0, 1s. So all these numbers, when you do these calculations as you go down here, becomes 0 or 1s. Now what we can do in order to look at all of these, we can simply focus on anything that is active, meaning has a 1 here, and ignore the zeros. When you do that, these are the numbers we're going to be looking at. So those are the ones you sum up. This is the verification, by the way. This is the number you're getting. So I created a C++ program in Visual Studio, and I used 2022 version. And as you can see here, I'm just doing some includes here. And I'm not going to dwell on what this means. What I want to show you is the way it handles the memory, because that would be similar to what you see in Go. So if you look here, you can see this is the main function, and here is my array. We're using a vector in this case. This is a standard library in C++. So I'm creating a vector of int, call it vec, and here I'm just loading the values directly in here right away. So don't worry about this code here, but the important thing is at this point, once we load it into memory. Now this is going to go into what we call a stack memory. So it will be sequential within a memory space. And as you recall, we used all these conversions from binary to hex to decimal, etc. So let's see, in VS Code, you can't do this. I can't create a Go program here in Visual Studio. So I created a C++ because that kind of illustrates the memory anyway. So I'm going to put it into a debug state, and it's going to load up. And as you can see, it loads this memory space. Now, what I can do here, I can go into debug menu, Windows, and go down to memory here and just choose memory 1. And that is what you just saw. Now this is just so you can move up and down the code. Now notice here, it has an address, and you might recall that we talked about hexadecimal leading with a 0x and then some bunch of stuff. Now, in order for me to figure out where I can find this stuff, I can hover over vec here. And when I click this guy and go to allocator, you're getting some bunch of stuff here. So I'm going to copy this. I'm going to just paste it into this memory panel. And I'm going to backspace it till I get to my first. So I'm going to keep backing here. And I'm going to stop right there. And then I'm going to remove everything in front of that, like this. So now I got a memory address, which is the hexadecimal portion of this. So when I hit enter now, you see there are some digits and stuff here. But there's only 2 columns. Remember, I want 4 columns. So let's set up 4 columns and see what that looks like. Okay, it looks a little better. Now I can also right click here and get rid of some stuff. I don't want to see all this stuff in the end here, so I'm going to delete that. Now right now I got just some numbers. So what I want to do is I want to set up 5 columns. Now I got some more stuff. Notice these are hexadecimal representations. So what I can do, I can manipulate this so I can see it in the format I want to find out what it is. It's not 1 byte integers. I need 4 bytes, right? So when I change that, this looks familiar, doesn't it? Isn't that the number we started out with from the top here? Let's go and look. So we went down here and we took this guy right here. So it's 012 FA58. So let's see what we're looking at. 012 FA58C. That looks very similar, doesn't it? So at this address here is where it stores sequentially these numbers. However, it doesn't really read well. But notice the last one kind of looks familiar because there's a bunch of zeros here. But right now we're displaying it as hexadecimal. Now when you work in C and some of these languages, there's something called a signed integer and unsigned integer. When you use a signed integer, meaning it includes the sign. So if you have a negative number, you'll see that negative number. So you should only use this when you have negative numbers and positive numbers. So what I can do is I can change this to, say, a signed integer. And notice now, we're getting our numbers that we had in that array, as you can see. Even the negative version of the number. Anyways, you get the idea. So you can use this and you can hover over here, get the memory address. And this is going to become important when we get into pointers. So I just want to show you this trick that you can actually track your memory position here. And you can also change values and you'll see the changes in this memory panel. That's the end of this video. I hope you like it, and if you do, give me a like and consider subscribing to my channel. It'd be fantastic. We'll see you in the next video. Thank you so much.